research is mainly focusing on soft electronics and energy devices, specifically focusing on piezoelectric and triboelectric nanogenerator, self-powered devices and soft robotics. So he have accomplished with several high quality and high impactful publications ranging from advanced materials, nature communications and advanced energy materials, etc. So we are much privileged to have Dr. Kaushik Parida as our today's speaker for this FDP program. So I hope all the participants will make use of the resource person and the research work which he is currently doing in IIT Roorkee. So we welcome you, sir, for your talk for today's FDP program. Please.
Okay, thank you, Dr. Vivek. I'm here at IIT Roorkee, the Center for Sustainable Energy and the Department of Polymer. So, first of all, I would like to thank organizers for inviting me. I would like to thank all the senior faculty members and all the faculty members of the university and my dear students. So, today I'm going to talk about wearable electronics, specifically energy harvesters. Okay? So, how many of you are from electronics background? Okay. What else background do you have? Like material science, physics, physics. Anybody else from any other stream? Mechanical. Fine. Okay. So, if you talk about electronic devices have made a huge progress in the last 50 years. Right from the invention of transistors to the current sophisticated electronic devices. Okay. In the last 50 years, the value factors for these electronic devices has been miniaturized, which is based on Moore's law. Okay. However, currently the Moore's law is coming to an end. We cannot further reduce the channel length of the transistor beyond 2 to 3 nanometers because quantum effect will dominate. Okay. So what is the future? What is the future of electronic devices? The future is popularly called as one-gap move or diversification. Okay. It is the addition of recently COVID-19 happens, right? We wanted to monitor the body temperature. So can we envision a condition where we can continuously monitor the temperature of the human body without feeling any discomfort, and if there is an abnormality, the information will be directly sent to your doctor, right? So we need this kind of wearable electronics, implantable electronics, so that we can continuously monitor human health. The second implication is personalized electronics, right? Samsung has already started commercializing flexible electronics. Okay, we are moving towards a technology where electronic devices will not be a separate entity. It will be an integral part of the human body. For example, in future, maybe 10 years down the line, mobile phone will not be a separate entity. It will be somewhere integrated out of the human body, and we can just tap it to use a mobile phone. Right? That's the future. To realize this future, we need a wearable and deformable or implantable energy harvester, right? Okay. So if I talk about energy harvesters, there are two kinds. One is piezoelectric energy harvester, which is based on the mechanism of piezoelectricity. Well, piezoelectricity is known to us for the last 100 years. Okay. What we have this very intrinsic to the material. These materials have a dipole. What is a dipole? Dipole is a positive charge and a negative charge separated by space. Okay. A material can have this dipole. For example, water has a dipole, right? H2O has a dipole. Oxygen has negative charge. Hydrogen has positive charge. Okay. Now, if I take a polymer, I have a polymeric chain, and onto that chain I attach, suppose hydrogen. Hydrogen is positive charge. And on the bottom of it, I attach fluorine. Fluorine is negative charge. This will create a dipole, right? Now, when I apply mechanical force, there will be a change in the dipole movement, right? When there will be a change in the dipole movement, a potential gradient will be created. Now, this potential gradient, okay, will create a voltage. Okay, and this voltage can generate current out. This mechanism is known to us for the last 100 years. Okay? And for the last 100 years, we have been working on to improve this technology. Okay. During 2006, people started to use nanomaterials. Everybody know what is a nanomaterial? Anybody has doubt? Okay. People started using zinc oxide nanorod in 2006, and they observed when they make this piezoelectric device, they will generate very high amount of voltage and current. Okay. However, the performance was still low. The energy harvesting performance was still very, very low. So in 2011, now when they had this triboelectric nanogenerator, this is based on triboelectric effect. So have you all experienced triboelectric effect? Okay. When you were kids, you have seen that we take a scale and rub it on our head, right there, and we basically forming a closed loop. Understood? Huh? When I cut it, the device is dead, the loop is open. When I join it, it starts healing and the device starts working. So we are able to make a conductor which is stretchable and self-healing in nature. Okay? Okay. So finally we wanted to make the device, right? We wanted to make an energy harvester which is stretchable and self-healing in nature, right? So finally we made the triboelectric device. Okay, now when I talk about triboelectric devices, triboelectric nanogenerators, it has made significant progress in the last 10 years. Okay, it started in 2011 and now within just 10 years, it can be used in multiple applications. For example, we can use as electronic skin. We can put it on our skin, we can just tap it and it can power LEDs. We can use for wind energy. We can generate energy from the wind. The wind can flow, right? And from the flow of the wind, we can create energy and power some devices. In fact, we can generate energy from walking. We can walk on the device and this can create energy. We can also put that device inside the body. For example, we can put it on your heart, right? Every time the heart beats, we are able to generate the voltage. So it can be used to power the pacemakers. Understood? Okay. Okay. Now you said, how come a polymer is stretchable? How come a polymer is healable? Right? Can any of you name a polymer which is healable or stretchable? Have you guys seen? Yes. Can you guys give an example of a polymer which is stretchable and healable in nature? Huh? PVDF. EVA. No, it's okay, it's fine. See, it's important to answer. No one knows anything. I also don't know anything. Okay? Every one of us are just learning, right? It's okay, don't worry. You want to say something? Okay. So basically, have you seen atta? All of you seen atta, right? Huh? Atta is healable or not? If I remove atta and attach it, get attached. Atta is healable? Huh? Have you seen the glue from the tree? Have you seen that? You cut the glue, take it out and put it back. Okay? How many of you have chewing gum? It is chewing gum. Chewing gum is stretchable? Healable. Right? Why it is working like that? Why these polymers are stretchable and healable? Because, okay, none of you are from chemistry background, so I know it will be difficult for you to understand. I'll just tell you brief. Okay? There is something called bonding. Okay? In polymers there are bonds, right? Some bonds can break and again it can form. That is called multivalent dynamic bonding or hydrogen bonding. Okay? Now what happens? Suppose I have some polymeric chain. I have some hydrogen bonding between the chains. Okay? Now when I stretch, this bond will get broken. Okay? Bond will get broken. And when I remove it back, the bond will form again. The same thing is happening in your atta. Same thing is happening in your chewing gum. Okay? There is a bond. When I break it, cut it, bond is breaking. And when I put it back, bond is forming again. Simple. Okay? I am not going to the chemistry part. So, what we could do, we could make a material which is not stretchable at all, and we could stretch up to almost 5000%. Okay? It is like a rubber. I'll show you in a video. You see? You could stretch it. Okay? You could stretch it. It is also transparent in nature. You cannot see this. And we can also take it back. Okay? So we could make a polymer which is highly stretchable in nature because of the multivalent dynamic hydrogen bonding. So we did the mechanical properties. I'll not go into the details of it. Basically, what we observe, this polymer has stretchability very high, almost 5000%. But the stiffness is comparable to that of the human skin. Okay. That means we can integrate that onto human skin. But the energy required to break our material is much higher. So it is better than the human skin because it will not get fractured easily. If you cut it, it will not break. Okay. Okay. So we also observed that, like we cut it, we heal it. We did a lot of studies like mechanical property before and after healing. I will not go into the details of that. Okay. So finally, what we did, we made energy harvester, which is a triboelectric nanogenerator. For the triboelectric nanogenerator, I have already said we have two polymers, right, of different surface charge. When I apply mechanical force, there will be this two surface charge of opposite charge, okay, right. When I apply and remove the mechanical force, it will come and go, right. Two surface charge of opposite charge is attracting and repelling, right. It's coming and going. So it will create a potential gradient. This potential gradient will create a voltage output. Okay. So this device, on an application of mechanical force, will generate around 100 volt and a current of around 4 to 5 microampere per centimeter square. I can show that in terms of a video. If I just tap a human hand, okay, it can generate this kind of voltage. Okay. We can also use to power LEDs. Okay. You can see just by tapping, I am able to glow the LEDs. Okay. Okay. Then what we did, we also wanted to demonstrate that we are able to make a device stretchable. So we measure the performance by stretching it. Okay. So what we did, we measured the performance by stretching the device. At various percentage of stretchability, we measure the performance. Okay. And we observed that of course there is a decrease in the performance, but still, even at almost 2500%, we are able to get some kind of voltage. This shows that we are able to make a device which is highly stretchable in nature, but is still able to generate very high amount of voltage and current. Okay. We also try to evaluate by damaging it, okay, damaging it and healing it. We first measure the performance, then we damage it, then we heal it, and then again we measure the performance. And the performance was almost similar, right? Well, what is the application? What is the use? We can use a different physiological condition. For example, we can put it on a wrist, right? We can measure the pulse before and after exercise, right? It is similar to an ECG. You don't have to go to the doctor to do the ECG. You can just put the device onto the band, onto your hand, and it can measure the ECG, right? In fact, we can decode what you're trying to speak. For example, I put my device on the human neck, right? Every time I speak different words, you can generate different kinds of voltage, right? So, if suppose somebody is not able to speak, he is speech impaired, right? We can, based on the movements of his this vocal cord, we can translate the map what he's trying to speak, right? That is the application of this kind of devices. Okay. Okay. Now, is anybody aware of 3D printing? Is anybody aware of 3D printing? Okay. Now, if you want to make electronic devices, we have to print it. Right? We have to make that. Right? There is a different new technology called 3D printing, 3-dimensional printing. What is that? We can print 3D objects by 3D printing. Right? So, using these 3D printers, we are able to fabricate these devices. For example, like this. Okay. Designs onto a device. Okay. In fact, we were also able to print on 3-dimensional object. For example, we took a wire, like a bottle, right? We were able to print a device onto the bottle. What does that indicate? It indicates that we can directly print a device onto the human body, right? A human body is 3-dimensional in nature. Okay, so we can directly print our device onto the human body. Okay. Okay. Yeah, so we went ahead and published this paper in a good journal. Okay. Now, I have been telling that we need a metallic conductor, right? Metal. Can you think of a device which don't need a metal? Can a device work without a metal, without a current connector? Okay. So what we did, we thought of making a device by replacing the metallic current connector. Okay. What we did a finite experiment. We took a balloon and we put water inside that. And we insert the electrode and we try to tap it. We observe that it is generating some voltage. Okay. Then we realize that water can also act as a conductor. It is not an electronic conductor, it is an ionic conductor. Okay. So water can also act as a conductor. Okay. Now how to use water in the device? Water will leak out. Secondly, this is a mechanical device. We need to apply mechanical force. We cannot use water, right? How to solve this? So what we did, we used a hydrogen. So do anybody knows what hydrogen is? How many of you know hydrogen? Okay. How many of you had jelly? When you were a kid, you eat jelly, no? It used to come in the jelly box. That jelly is a hydrogen. Okay. What is the hydrogen? Hydrogen is basically a polymeric matrix infused with water. 99% is water. Okay. Now this jelly, and most of you have seen the jelly, right? The kid when you used to eat. The jelly have some mechanical rigidity, right? Mechanical strength is there. You touch it, you can touch it. It's not like water. But it is 99% is water. The jelly contains 99% is water. Only 1% is polymer, 1% is material. Okay. So we made something like a jelly, like a hydrogen. Okay. Hydrogen is basically, you cannot even see it. It's transparent, right? It is 99% is water, 1% polymer is there. So now we can apply mechanical force. Okay. Now this hydrogen has also hydrogen bonding. Now when we cut it and attach it, it will again heal. Have you tried with the jelly? Huh? The jelly will also, if you cut it a little bit, attach, it can also heal. Okay. So we use this jelly as a current connector by replacing the metal. Okay. So what we did, basically what we did, we remove the metal and use this jelly. Okay. Something like a jelly. Okay. What was happening? Now, to understand the mechanism, when we have a metallic current connector in the triboelectric nanogenerator, what is happening? On the top, surface charge is being created. It is getting electrostatically induced in the metal. Okay. But in the hydrogen, we have ions, positive and negative ions. Just like water, salt solution. We have ions. We add 1 molar salt in water. We get sodium and chloride ion, right? And these ions are moving inside the hydrogen. Okay. When I get a charge on the surface, what is happening? Opposite charge ions. For example, I hit a negative charge on the surface. Positive charge ions get absorbed at the interface of the hydrogen and my polymer. And the negative charge ions get absorbed into a wire attached. Basically, the charges are getting separated. Okay? Charges are getting separated and getting absorbed on the expected interfaces. And because of that, we are able to extract the charge. It's a little bit difficult to understand. Okay. Try to understand in a way that basically this hydrogen or the jelly just trying to collect the charge from here and just removing it. Okay? You able to understand? Oh. Okay, so we are able to go ahead and publish this paper in a good journal. What are you able to do it? Can we use this device? Can we use this device to power something? So what we did, we tried to tap it and we could power this digital watch. You can see, you can keep on tapping it and at some time the digital watch will get switched on. Okay? So by just tapping it, you can power the digital watch. In fact, by tapping, we could able to power few LEDs. Okay? Okay, we are able to publish this in a very good journal, like very high quality journals. With that, I would like to thank every one of you for your patient hearing. If you have any questions, I would be happy to answer them. Thank you. Thank you. Yeah, if you have any questions, I will be happy to answer them. It's okay, look, sit down.
What was the effect of temperature on this? How much temperature can withstand this polymer?
Yeah, it's a very good question. Okay, so basically his question is that what is the effect of temperature on these devices? Okay, can it withstand very high temperature? We need to for that we need to understand what are the components. The components are polymer, right? Now polymer cannot withstand very high temperature. For example, the kind of polymer I used, it cannot go beyond 90 degrees Celsius. Okay, but there are certain polymers like Kapton, polyamide, right? These are very high temperature sensitive, high temperature tolerant polymers. For example, it can withstand up to 200 degrees Celsius. Okay, so basically these are for application at room temperature conditions. Suppose you want to use it for space application, we cannot just directly use it. We can use Kapton-based devices. Okay? Yeah. If there is any other questions?
So can in the metal, so you have told to convert the liquid to the metal balls. So the same process can be applied to any type of polymer?
No. It is very specific to the technique of indium gallium. Because it is forming a participating oxide. Okay. It is very, very unique to this material. It cannot be universal. This is a very interesting phenomenon. People are still trying to explore why this is happening, and there is a lot of research on this, but this is not universal. Okay. Yeah. Any other questions? Any other?
I think okay. That nano-sized liquid space while stretching, it is breaking and making a contact between the cylinders. After releasing, what is happening, sir?
Excellent question. Okay, excellent question. So the question is, suppose I have two silver flakes. Okay, I have liquid metal particle. Now when I stretch, this particle is ruptured. Okay, and it is forming an anchor between the two separated silver flakes. Now when I release it, like liquid can take the shape of the container, right? There is space available, right? It can come back. But what is happening? What is happening is, it is again forming a passivating oxide coating. It is again forming a particle.
So its shape is
Regaining back. Because water can come back, right? And if you keep it, it will again form a passivating oxide coating. Right? So because of that, it can again regain its original shape. It's very, very, very interesting question.
Have you tested any cycles for that? How?
Yes, we have done multiple cycles. Yeah, I didn't show that. You see the cycle number, okay? We could go for up to 10,000 cycle of stretching, right? Even after 10,000 cycles of stretching, you can observe there is no significant change in the resistance. Okay? Yeah, it's a very good question.
So
Yeah.
other than silver flakes, can we have any other material?
Yeah, definitely. Definitely. We can use different types of material.
As a conducting?
Yeah, we can.
Because this has a like a liquid phenomena what you have told. Does any other such
Yeah, I mean, for example, in case of silver, you can use copper. You can use copper flakes, nickel flakes. Okay. Yeah, gold flakes is very difficult to make. Gold nanoflakes are very difficult to make. So people, I mean, yeah, 1 year back, I don't know, we were not able to make, but recently I don't know. But yeah, gold flakes are very, very challenging to make. So that's why people have not used that. In case of silver flakes, we can vary. But in case of liquid metal, you cannot change. In case of liquid metal, I cannot change. I mean, there is no other material can behave like that. Yeah, anything else? Okay, if there is no other question, I would like to thank all of you for your patient hearing. And if anything else, we can discuss in the later. Okay, thank you.